Last week, we were doing radiation from oscillating charges, and in particular, we focused on a point dipole radiating energy. We will continue that study this week and take different examples of how radiation comes out from different systems. So, in this lecture, I am going to talk about radiation from a thin wire antenna. Through these different examples, I expect you to learn how to deal with retarded potentials and the fields arising from them in a proper manner. So, the problem we are tackling now is there is a thin wire on which we have applied voltage in the middle. Its length is 2d and it has an oscillating voltage applied to it, so that the current in this is a function of z. I am taking this direction to be z is equal to I naught sine of k d minus mod of z, and it is in the z direction. So, notice that I at z equals plus or minus d is equal to 0. There cannot be any current at the ends, and the full time dependent current is I z t equals I naught sine of k d minus mod z e raised to minus I omega t. So, it is an oscillating current, and we will see how it gives rise to radiation. The corresponding J R t will be given as I naught sine of k d minus mod of z e raised to minus I omega t delta of x delta of y in the z direction. Why have we taken a thin wire? We have taken a thin wire so that there is no confusion about how the current gets distributed over the cross section of the wire. So, thin wire means no concern about distribution of current across the cross section of the wire. Now, we will again go the same route as we have been doing. We will calculate A and phi, but first let me write what the corresponding charge density would be. For the charge density, we use the continuity equation, which gives me d rho dt is equal to minus gradient of j, and therefore, on the left hand side I am going to get minus I omega rho r t, which is a function of z only, and on the right hand side I am going to get I naught k sine of k d minus mod z. That is going to be the charge density times the time dependence e raised to minus I omega t. So, we will calculate the vector potential A r t from the current density J r prime t retarded divided by r minus r prime d v prime, and we will calculate the electrostatic or the scalar potential as 1 over 4 pi epsilon 0 integral rho r prime t retarded over r minus r prime dv prime. This later part I am going to actually leave for you to complete as an assignment problem. I will just do the first part so that you know how to go about doing this calculation. So, let me just make this antenna again. There is this little gap from which the voltage is being applied. This length is d, the other half length is also d, and I am calculating A at r and t, which is equal to mu 0 over 4 pi integral j r prime t retarded over r minus r prime dv prime. And because of the delta functions and j being only one dimensional, I know that j dv prime can be written as I dz prime in the z direction, and therefore, the vector potential A r t is going to be equal to mu naught in the z direction, which is a constant direction, over 4 pi I naught sine of k d minus mod z e raised to minus I omega t retarded divided by r minus z, should be z prime, and this is integrated over z prime from minus d to d. This is the calculation which I can write as mu naught I naught over 4 pi in the z direction integration minus d to d dz prime sine of k d minus mod dz prime e raised to minus I omega t retarded divided by r minus z prime in the z direction. Now, we will take the approximations that we usually make. We are talking about radiation zone. So, r is much greater than d, and therefore, I need to keep only linear terms in d. So, I am going to write modulus r minus z prime in the z direction as equal to square root of r square plus z prime square minus 2 z prime r cosine of theta, which I can roughly write as r minus z prime cosine of theta. And as we have been making that physical picture, here is the antenna, and I am at a large distance r from here, and the z prime is very small. So, all I am doing is this distance, I am taking them almost to be parallel. This is z prime cosine of theta. I am looking in theta direction, and therefore, I just subtract that point out. And therefore, t retarded, which is t minus mod r minus z prime vector over c, is going to be t minus r over c plus z prime over c cosine of theta. We have gotten all the ingredients to calculate the vector potential, which now can be written as A r t equals z unit vector mu naught I naught over 4 pi integration minus d to d dz prime. I get sine k d minus mod z prime e raised to minus I omega t minus omega r over c times e raised to plus I omega z prime over c cosine of theta divided by r minus z prime cosine of theta. I will rewrite this on the next slide. So, we have gotten A r t equals in the z direction mu naught I naught over 4 pi integration sine of k d minus mod z prime times e raised to plus I omega z prime over c cosine of theta divided by r minus z prime cosine of theta dz prime, and is multiplied by e raised to minus I omega t minus r over c, which I can take out. Let us just focus on the integral, because rest everything is independent of z prime. So, I will leave it as is and focus on this integral. The integral is integration minus d to d sine k d minus mod z prime e raised to I omega z prime over c cosine theta over r minus z prime cosine theta dz prime. By the way, k is omega over c. So, I can replace omega over c everywhere by this k and take the binomial expansion of 1 over r minus z prime cosine theta to write this as equal to, I am still focusing on the integral, minus d to d sine k d minus mod z prime e raised to I k z prime cosine theta divided by r, and then I multiply by binomial expansion 1 plus z prime over r cosine of theta dz prime. Remember, if I am talking about radiation, I am interested in the term which is proportional to 1 over r. So, need A proportional to 1 over r for radiation. So, this implies neglect z prime over r cosine theta term, and therefore, I can write this integral as minus d to d sine k d minus mod z prime e raised to I k z prime cosine of theta divided by r dz prime. So, even this r comes out now, this r goes out, and therefore, I am left with a very simple integral. So, let me write A all over again. So, you collect all these terms and you are going to get A r t as equal to, in the direction z, mu 0 I 0 over 4 pi. Now, that r I have taken out, e raised to I omega t minus r over c I have taken out, and I am left with this integral minus d to plus d sine k d minus mod z prime e raised to I k z prime cosine theta dz prime. Let us write this integral in two parts. I am going to write this as minus d to 0 sine k d plus z prime, because mod z prime. So, it becomes plus for negative values, e raised to I k z prime cosine of theta dz prime plus integral 0 to d sine of k d minus z prime e raised to I k z prime cosine theta dz prime. I am going to change the upper integral now, this one, by replacing z prime by minus z prime. So, z prime is replaced by minus z prime. I can always do that, and then this integral becomes 0 to d sin k d minus z prime e raised to minus I k z prime cosine theta d z prime. And then I combine these two integrals and I get this integral to be, this integral is from minus d to d, this whole thing d z prime equals 2 integral 0 to d d z prime of sine of k d minus z prime times cosine of k z prime cosine theta, which is a very simple integral to do, because I can write this integrand as this is 0 to d 2 times d z prime, and this integrand becomes sine of k d minus z prime plus k z prime cosine of theta plus sine of k d minus z prime minus k z prime cosine of theta, this whole thing divided by 2. So, this is equal to minus d to d d z prime sine of k d minus z prime 1 minus cosine of theta plus sine of k d minus z prime 1 plus cosine of theta d z prime. This is a very simple integral to do, and I made a mistake here. This should not be minus d, should be 0 here, and this comes out to be cosine of k d cos theta minus cosine of k d divided by k sin square theta. I leave the steps in the middle for you to work out. It is a really straightforward integral. Now, we substitute this for calculating A, and we get A r t equals z mu naught I naught over 2 pi r e raised to minus I omega t minus r over c times cosine of k d cos theta minus cosine of k d divided by sin square theta, and there is a k here. This is the vector potential in the z direction. I may have missed a factor of 2 somewhere, please check it and correct it, and this is the answer you get. And from this I can calculate B, which is equal to curl of B. Keep in mind, when you take the curl, this curl operator also acts on this e raised to I omega t minus r by c. In the same manner, I can calculate phi r t. Phi r t is going to be equal to 1 over 4 pi epsilon 0 integral minus d to d d z prime rho z prime t retarded divided by r minus r prime. And from this I can calculate E field to be minus d a d t minus grad of phi. Oh, I should have written A here. I can also calculate E field from the B field. So, E in that case would be equal to B cross r times c. In any case, I mean, once you do these calculations, you can always find one of the ways to do it. Keep in mind that we are after radiation field. So, we wish to calculate radiation field. Which from whatever you have done is going to be E perpendicular to r and B also perpendicular to r unit vector. So, whatever calculation we do for E and B from these potentials, finally, we have to take the perpendicular component. For that, somewhere along the line, you will have to take E calculated cross with r cross, and similarly for B. All those calculations I will leave for you, and once you do this, you get your power also. Power is given by 1 over mu 0 E cross B per unit area. You have been doing these calculations for the curl and time derivatives. That is why I am not doing it now. I will take the limit for a very small antenna. So, we found that A r t is equal to z mu 0 I 0 over 2 pi r e raised to minus I omega t minus r over c times cosine of k d cosine theta minus cosine of k d divided by k sine square theta. If I take the limit of this antenna being very small compared to the wavelength. So, remember k is omega over c, which is 2 pi over lambda. So, if I take k d to be much smaller than 1, this means d over lambda to be very small in comparison to 1. So, antenna is very small. In that case, the vector potential A r t would be equal to z mu 0 I 0 over 2 pi r e raised to minus I omega t minus r over c times, now inside I have to do cosine expansion. So, I will keep terms up to second order. So, it will become 1 minus k square t square by 2 cosine square theta minus 1 plus k square d square over 2 divided by sine square theta. This one cancels and you get this equal to z mu 0 I 0 over 2 pi r e raised to minus I omega t minus r over c times k square d square divided by 2. That is the vector potential. The point that I was making about the E field, let me make it through d E dt. If I were to calculate d A dt, this would be equal to z minus I omega mu naught I naught over 2 pi r e raised to minus I omega t minus r over c times k d whole square divided by 2. Now, you see this d A dt is in the z direction. If I were to take its r component, what I would do is the radiation component, I would take this d A dt, take r cross this cross r, and that will give me this whole thing in the theta direction times the sin theta term. I will let you work it out. That is what I meant, that you got to take the component which is perpendicular to the r direction, and that is the electric field component corresponding to radiation. So, quickly let me conclude this. Lecture by saying, number 1, we have considered a thin wire antenna and calculated the vector potential for this. Two, we have taken the limit of antenna being much smaller than the wavelength. Finally, left the calculation of scalar potential for you. Thank you.